Good afternoon. We're just going to give it a few more minutes to wait for people to join, and then we will go ahead and kick off the webinar. We'll just give it one more minute, and then we'll kick this off. Okay, good afternoon, and thanks for joining us today. My name is Kristen Prokop. I'm the Senior Marketing Manager here at M2 Technologies. Today we have Blake Jensen, a Technical Sales Specialist from Autodesk, joining us. He'll be presenting on Nesting, Utility, and Inventor, and then at the end we will open this up for some Q&A. Blake, take it away.
All right, thank you, Kristen. Like she mentioned there, I'm a technical sales specialist with Autodesk in our design and manufacturing group. Just so you have a quick understanding of my background, I'm a mechanical engineer with a fairly wide range of industry experience, and since joining Autodesk, I've become an expert in our excuse me, manufacturing and design technologies. So today we are here to talk about nesting and how that integrates with the Inventor platform. So first, let's start with the definition of what nesting is. Essentially what we're doing is we're locating multiple shapes of different geometry or the same geometry into a stock material in order to maximize material usage and yield. This is most useful for those working in sheet metal manufacturing, but is also of good use for people working with wood or plastic or really any other sheet good. Today we're going to focus on primarily sheet metal nesting for use with a laser cutting manufacturer. So let's talk about some benefits quickly. Number one benefit of using Inventor Nesting over any other nesting solution is in-canvas CAD integration. So what does that mean? That means that we are using a nesting platform that fits directly inside of your Inventor window. It's simply switching a tab in your ribbon and off you go to nest your parts. We're streamlining the design to manufacture process by allowing you to work in a single environment and really gain efficiencies through associating your nesting output with the CAD file design that you've created and maintaining that familiar user interface across multiple environments. Another benefit is automatic nesting. So the old way of doing things is manually nesting shapes, and we'll show a little bit of that coming up here, but you know, we would take a shape, drag it into our stock, copy it as many times as we could, and you know, whatever we ended up with was good enough. You do as well as you can, but you didn't have a ton of automation or computing power behind it. And along with that, the nesting tool in Inventor Nesting gives you detailed nest reporting, which not only gives you that insight into how many pieces are we nesting, what's our inventory level, but really allows you to see at a detailed level the cost per part in raw material. So real quickly, here's the general flow of data through this design and manufacturing process in Inventor and Inventor Nesting. So we started in Inventor Design where we're creating those parts and assemblies. Primarily, these are going to be sheet metal parts, but the Inventor Nesting tool will take in others. So we'll design those parts, create our flat patterns, and then we bring those into Inventor Nesting, where those parts are nested into a sheet, grouped by thickness automatically, and yield is maximized based on some parameters that you input. Once those nests are generated, we can then create reports that give us that insight I mentioned earlier into part cost, nesting orientations if we're concerned about things like grain direction, so on and so forth. And then after we leave the nesting environment, we go into Inventor CAM, which is again really just switching tabs in the Inventor ribbon, where we can generate those 2D cutting toolpaths and publish our NC code to actually send out to the machine and cut the material. So without any further ado, we're going to jump right into the live demo portion of today's webinar, and we are going to go right into Inventor 2020 here. Let me just verify that that's showing up. Okay, great. This is the chassis of a PC tower computer. As you can see in the model tree here, this is mostly sheet metal parts with some non-sheet metal components as well. This assembly is clearly in the folded orientation of any given part. And because this is Inventor and it's an associative CAD platform, I can jump into any of these parts and do any sort of detailed inspection, design modifications, whatever I need to do here. So when I go to create that nest, what I like to do is just start at my top level assembly, because generally speaking, I want to create nests for a particular design. So in this design, I go to my top level component, whether that's a part or an assembly, right click, and right here I go to create nest. Now, just to save a little bit of time, so you're not watching my computer think about this, I've already created these nesting results and extracted geometry. So here we go over to the nesting environment. And you can see that the Inventor Nesting tool has pulled out the geometry sources here, flattened them, and grouped them by thickness. Those thicknesses are set up here in the process material library. In this case, I have 5 materials. They range in thickness from 19 thousandths of an inch up to about an 1/8 inch. They have materials assigned, densities, nesting colors, and then we can go further and define the actual size of the sheet, whether it's a rectangular sheet or a roll, the cost of each specific material, and change those length and width dimensions to match up with your actual stock. For now, I'm going to leave this at 200 by 40, but we can adjust that later. So if we go into this particular nest, we can see that I've got each sheet is divided, and we have the thickness of each part is corresponding with each individual sheet. If we look at this nest 2, for example, I can see that I'm taking an assembly of that PC tower. I'm taking a quantity of 10 of those assemblies, and I'm nesting this into this one sheet. Now, underneath this quick nest output, I can see how many of each part is included in the nest, the overall size of the sheet at 200 by 40, what the length of the cutout section is at 138 and change inches, and the length of the remnant at approximately 61 inches. Now, if that's not enough, and I want more insight into my nest here beyond just my overall nesting efficiency, number of parts and number of sheets, I can come over here into this report. So this is under Nest 2, and you can see that it highlights here if I hover over Nest 2. I can go to Report, go into my Properties, and let the Inventor Nesting tool generate a report for me. Now, this is the default report. It's pure HTML. It's highly editable and configurable by you, the end user, to show or hide the data that you find valuable and the data you actually want to use. So in this report, I get a quick look at the number of components, the same as my graphical output for the nest here. I get a look at my nesting properties, both goals and actual usage, my thickness, my density, my material name. I can see how many of each part in my source I've got, what the orientation is, what the allowable orientations are. I can tie this into my inventory. So I'm using one sheet at 200 by 40, and this is an arbitrary number here, but this could be tracked over time so that you are tied into your actual material inventory rather than not having that insight. I can also scroll down further and skip past some of these individual orientations and look at my sheet part and cost summaries. And I think this one right here is the most revealing chart on this whole report in my experience. So if we have an assigned cost for our sheet, in this case it's $1,000, and we're assuming that we're not going to use the remnants, I can look at this part cost pie chart here and see that my hard drive bracket is responsible for 23% of my total cost. So not only can I see the cost for my sheet, I can go in here and I can actually see what the cost is per part. I can see what parts have been excluded, what my efficiencies are, and really get all kinds of insight that I wouldn't have if I was doing this manually. Now, I can print this out as a PDF or on paper, and then you can track this over time to get more historical insight into your nesting efficiencies. Now, I did say that this is already created, but what happens if I need to make a change? So I can come in here to this Nest 2 properties, and let me just resize that window for us. Item separation and frame width are an important thing to keep track of in sheet metal manufacturing. I can't put the boundaries of my parts exactly right on top of each other because I'm always going to be limited by the width of cut of my laser cutter. In this case, I know I'm going to use a width of cut of 80 thousandths, so I'm going to go with a 100 thousandths item separation and a 1/8 inch item frame width. So that's the distance from the edge of the part. And when I hit OK, it's going to automatically recalculate that nest and update to my new geometry parameters. And we can see that calculating here. And for more detail, we can switch over into this Calculate Nest tab. Now it's just going to take a few more seconds. Keep in mind that we're seeing this take 25 seconds or so, but we're also nesting 60 individual components, and you can see that this geometry is now updated to maintain proper spacing between parts. That's a pretty quick process. So what does that look like if I had to do that manually? To show you that, I'm going to switch over into AutoCAD. And I've got a nesting stock of approximately the same size and my 5 geometry sources that were included in that same nest. Now, to nest these, I would really take that piece, copy it, paste it, maybe several times, and I could move this around. But you can tell already that this is going to take me a lot longer to get those 60 components nested and accurately spaced. And I just don't have the same level of control that I have in Inventor nesting. I absolutely could do it, but it's going to take time. And it's just, you guys are busy. You've got work to do. Inventor nesting is a much more efficient tool. So switching back into the nesting environment, if I need to take this nest and send it to, let's say I need to send this nest to an outside manufacturer. I can go back into my nest. All I need to do is click on this sheet that I want to actually manufacture, and I can go to export. And what that's going to do is it's going to save this sheet as a DXF file or a .msi nesting file. As I'm sure you guys are aware, most laser cutters will work natively with DXF files. So you have that flexibility to output your finished nest as a DXF. But I'm going to do you one better. Staying in the Inventor workflow, in the Inventor space and product design manufacturing collection, what we can do is we can actually take this nest, create a 3D model. I'm going to go with a multi-body part file here, just to keep things in a single part that I can keep track of, and then hit OK. And what that's going to do is it's going to create a 3D model inside of Inventor still. You'll notice that for this entire workflow, I haven't had to leave the Inventor workspace. It's going to create a 3D model with all of my source geometry. It's going to maintain that nested relationship, and it's going to bring that into a new part file that I can create all of my cutting tool paths on. And this is taking a little bit of time to create this model here, so I apologize for that. Looks like I may have crashed my Inventor. These things do happen. Unfortunately, that's the reality of working live. Just get that started back up. Here we go. We'll go into a nested part that I've created already and save for this purpose. So you can see that I've maintained geometry. This is not the same nest we were just working with, but this is an example that we can use here. You can see that I've kept the geometry of the stock material and all of my embedded parts here. If I wanted to go over and create my 2D cutting toolpaths, all I need to do is switch over into the CAM environment. Actually, let's make sure that's disabled first. Switch over into my CAM environment, create a setup, select a cutting type operation, and my stock geometry. And that's just this solid body that we created on the output from the nesting tool. Hit OK. My setup is created here. And then I can move over into my 2D profile setup. Choose laser cutting over water jet plasma and laser. And I'm going to go with a through cut. And you can see here that I've got several options utilizing either feed rates of the machine or the actual quality of the cut. If it's a high, low, medium quality, if I want to etch bend lines into my my parts here, I absolutely can. In this case, I'm going to go with the through cut just to cut out the external and internal shapes of each individual component. I can set my curve width to 80 thousandths, or in this case, I'm going to go 1/16 of an inch, and I'm going to set the machine to use feed rates. In this case, 40 inches per minute for both cutting and lead in, lead out rates. Then I come over here to select geometry, and I can just, select whichever contours I want to actually cut out. So I'm going to go with those just for the sake of demonstration here. You obviously would probably want to go with the whole sheet or whichever components you wanted to cut out. In this case, I'm also going to add tabs so that my parts don't fall through the sheet, and those will be added automatically at a width of 10 thousandths, or I'm sorry, 100 thousandths. I can choose this to be anything I want at any spacing I want. They can go at specific points, or by distance. I'm going to go by distance. So when I hit OK, what happens is Inventor CAM, based on the HSM platform, is going to create that 2D cutting toolpath. And you can see that it's generating here in the background, and we're at 50% already for that profile. And what I can do once that toolpath is generated is actually simulate that laser cut. So I can get a look at what does this program look like to run. And from here, I can either adjust the parameters of the toolpath that I've already created, or I can look at the statistics. So this path is going to take 27 minutes to actually cut out these sheets or cut out these parts. So now between this toolpath simulation and my raw material cost that we saw in the nesting reporting, I have insight into both parts of what my parts actually cost to create, right? So I have the raw material cost from nesting, and I have the per hour cost to run my machine. Between those two, I can divide this out and figure out exactly what these parts are costing. Okay, so let's assume I'm happy with this toolpath. To actually create something useful, the NC code, what needs to happen is I need to run this through a post processor and then actually output the NC. So here I go with the post processing. It's just a button right here. It's going to search through all of my available posts in this folder here. And I do want to point out at this point that this is the library of post processors is extensive and 100% free from Autodesk. It is, we support a ton of different machines, a ton of different processes. Odds are really, really good that we have something out of the box that will run whatever machine you have today. So in this case, I'm going to go with cutting. I have two post processors set up. I'm going to go with this Amada laser. I can open this post processor to configure any properties that I want to change as is. I can choose my output folder here where to actually put that NC file, and then I can change some properties in that post processor here. In this case, I don't mind any of these properties. These are fine, but in a lot of cases, this is going to be where you change the what the machine is expecting for thickness of material, what sort of amperage output the laser is going to use, that sort of thing. So I'm going to go ahead and output the post here. And this is just a generic title, 1001.nc. And this is going to already exist, but I'm going to replace it. And then here's the output post, or the output NC code that matches up with the Amada laser post processor. So I'm not a machinist by trade. This sort of looks useful to me, but I do know that there are those of you out there that can look at this G code that's been created and read it like a book. Now, you can go through here, you can make your tweaks to your G code, you can do whatever you need to do, but this absolutely will run your parts as is. We can backplot this code so that we get some visibility, just like we had in the Inventor window. We can simulate this G code here, run through, and show what this looks like in real life. So in this case, that's the end of the NC code. As you can see, this is a fairly simple process. It doesn't want to go away for some reason. This isn't a real difficult thing to do, right? We can take our assembly, we can take our nested results, and if I need to go in and I need to create a new study, a new nesting study, or I need to change the number of components I'm nesting, I can either take this nesting study that's already created and create a new one. So that's what I'm going to do here. You've seen me run through the process, but now I want to show you in a little bit more detail of how to create this nest. So I'm going to go into create. I can choose which source files I actually want to include. If I don't want everything from my assembly, I don't have to use it. So I'm going to take all of these generic shapes, generic material shapes, and exclude those. So I'm only using my my steel and my aluminum parts. I can choose whether to use a single value or a single value. So that's how many of the entire assembly. Or I can do a multi-value and actually choose, you know, if I'm going from multiple assemblies, I can say I want to run 1 of this PC chassis, 2 of something else, 6 of something else, so on and so forth. In this case, I'm going to go with single value. I'm going to run 5 of those. I can choose my positioning of my nested components, set my desired yield, and how I actually want to utilize that material, whether it's minimizing length, width, or area. So once I hit OK, it's going to automatically create those nests. You can see here I've actually created a new nesting study. And if I hide the old one, the new one should be popping up there. And just like that, I've taken my, I've created a new nest. Oops, zoom back out. I've created a new nest with all of those same geometries, but I'm using different parameters and different overall nesting. I did mention earlier that I would go in and I would change my material library. So 200 by 40 is kind of a strange size. Let's say, what material was this one? This one was packaging 3. So on packaging 3, let's say instead of 200 by 40, it's really 96 long by 48 wide, a standard 8 by 4 sheet, and it costs $650. Just like that, it's going to recalculate when I tell it to. It's going to recalculate that nest with my new geometry. As soon as that updates. And now I've got actual material match again. I can see my remnants, I can see my total cost, my efficiencies, and all of that quickly and easily. So just in conclusion, with Inventor Nesting, this is a highly flexible, highly user-friendly, integrated nesting workflow that allows you to take your Inventor geometry, nest it in a sheet of material stock, and then quickly generate cutting tool paths that will facilitate the manufacture of your parts. And with that, I'd like to open this up to any questions you guys may have. I am all ears and more than willing to answer anything you've got.
Okay, good.
Okay, doesn't sound like we have any questions. Um, if anything comes up after this webinar, I know that's something that happens to me all the time. I have a hard time coming up with those questions live, but always think of something after the fact when I'm reflecting back on it later. Absolutely feel free to contact M2 Technologies, your authorized Autodesk partner. They are experts in this stuff by phone, web, or email. And yeah, thank you everyone for your time today. It's my pleasure to present Inventor Nesting to you.